Piramanayagam. Yeah, I just got it.
I think begin. Students are still coming, but I think let us not delay that program. We will start.
Hello.
So we have around offline we have around 30 online is
ठीक
so people are still not on the host will get together.
Post?
If they don't come to an understanding, they will start.
Why yet another
One more step. Come. Yeah.
Hey, Namade sir किधर है?
He's coming. I just met him outside.
Then how many places you roam around? He is in physical science and mathematics. I was in school of computer engineering. So the buildings are not in where? Oh, you are in Leicester. Yes, yes. Yeah, under his. One year I enjoyed there. My time people are there also. In a sea. Other place. Vesta institutes are very nice. In Singapore, Vesta institutes are very nice. They have multiple divisions or institutes. They are very nice. And they do good amount of research and products. Towards product. And Vesta usually do the joint or collaborations with NTU, NU, all those. So they are the middle. And
माइक को कैसे ऑपरेट करना पड़ेगा बस अगर ऑफ करना नहीं वो नहीं रहेगा इसको थोड़ा नज़दीक से बोलना है
ultimately, that was earlier. I don't know whether still. No, Tanmay, that's why he was telling me should sit there. That I was not.
No, Professor Niman, I just we both met him on the way. I just dropped him by the now. He just wanted to give him the office.
We should have told. Then I should have keep.
Sorry.
Well, I thought everyone available. Huh?
We are waiting for.
तो पहले 11 नंबर बस में चलते हैं.
अगली बार मैं ऐसे ही करता हूँ.
नहीं वो तो 11 नंबर बस में चलते हैं.
No, today he was rushing actually.
That is okay. Speed ज़्यादा बढ़ा दिया.
But see,
बस तो वही है.
I mean, he works actually quite fast, if I would say, because every day he works that one, you know, and comes.
He cannot work with Java directly.
He works even faster.
Right? He is laughing. You cannot imagine the way.
During one student orientation, I am the faculty advisor. I got to go and start going around the campus. Director already took them, and I cannot find him. The whole group is gone. So I can understand how fast he works.
Tanmay, you are doing Spintronics?
Yes.
I haven't checked it.
That's typically where the years are.
Why you are standing to come here?
I have to explain you.
Okay. Good morning, everyone. First of all, I want to express a warm and very hearty welcomes to everyone who are present here for the inaugural program of the prestigious GIAN course titled Spintronics Memory, Physics and Technology. To set up the tone for this inaugural sessions, I would like to invite Dr. Tanmay Dutta sir, our respected course coordinator, to deliver a brief introduction to the course and share with us the vision and objective behind organizing this academic endeavor.
So, good morning all. Good morning to all the guests present. Our foreign faculty, Professor Prem, all the students, all the participants who are gathered here, and also all the participants who are also joining us online. So, just to give you a brief about this course, the course will focus on the course will focus on, yeah, some of you are smiling, I can see that. That's how we begin, right? Okay, so the course will delve on some basics of magnetism and spintronics, right? Some of you, I think, are already aware of this domain. Some of you may not be aware, but we look forward to the fact that in the next 10 days you learn a lot, and at the end of this course you will be you would have definitely learned and gained some knowledge to take back with you. Maybe it will be helpful for your research or future academic endeavors, or maybe your job prospects, right? So that's what we look forward to. So we'll begin with some basics of magnetism and spintronics. Then we'll move to different kinds of spintronics based technologies, maybe different like MRAMs, MTJs, and so on. The basic phenomena that are behind these devices, right? And finally towards the different memory technologies, so including some existing technologies in terms of, again, MRAMs, the technology part of it, and also towards the future technologies in terms of the neuromorphic devices and other advanced memory technologies. Okay, so that is kind of the outline how we will proceed. You may have all received the lecture schedules, so that will give you more detail about it, and I think I'll leave to Professor Prem to talk more about the course. I would also like to mention that we were quite happy and overwhelmed by the kind of response we received with the registrations. We actually had more than 300 students and faculties across, who had expressed interest in attending the course. Unfortunately, because of different, logistics and transport disruptions that happened because of the conflicts in the recent weeks, many of the participants have requested to host it either online or postpone it. Unfortunately, we cannot postpone it, but we have allowed many of the students to attend it online. Many of the candidates are therefore joining us online. But thankfully, we are able to still cater to them. They are still able to learn, and offline or online, I welcome all of you. Learn well. Please feel free to interact, and we will get to know you more during the next 10 days of the course. Okay, looking forward to it. Thank you. I would now ask the dignitaries to please help us in lighting the lamp and inaugurate this course. Thank you.
You are the guest. You are the guest.
I would like to thank Dr. Tanmay Dutta sir for leading us in the lamp lightning. Now it's my pleasure to request Professor Sukumar Nandi sir, Dean of Administration, to kindly felicitate our esteemed foreign expert who has graciously joined us for this course. Thank you, sir. May I now invite Professor Sukumar Nandi sir to kindly share few words with the audience.
I know. Good morning to all of you. Those are online and offline participating in this program. My colleagues are here, including foreign colleagues. Okay. But why I told foreign colleagues, I was there also. So, in different school, once upon a time. It's nice to see that good number of participants physically present here as well as online. Today, India able to deliver lot of things recent past. If you look, lot of things we have delivered recent past, because we are now a country going to be developing country to developed country. That is first. Second, we are going for third largest economy, going to be. That is the target. And our research has taken a long dimensions, and we are able to deliver technology precisely recent activities by Government of India, we as a whole. The precise technology targeting a particular point and delivering without minimum causality needs our brainstorming, our future learning and future acceptability by the society as well as defense. So, whatever we do, we use for dual purposes. Definitely you work for some purpose, it can be used for some other purpose. Why I mention this? today memory technology, what I studied in during my journey in this technology domain was very, very rudimentary. We started with transistor, then SSI, LSI, like this. Now it is GLSI, correct? And then CPU technology went in one direction, CPU related or computer related, and memory technology went in another directions. Both are not going in that speed. However, memory technology is catching up. And because of memory technology, today computing ability we have. That is, today we are talking GPU with how much memory, anyone can guess? 80 GB, and some places, some people are talking more than 100 GB cards, GPU cards with that much memory. And that memory comes from research on memory technology. And today memory technology not only in whatever we are doing, the compute is also going towards the inside the memory or closer to the memory, that is near memory and in memory. That is, so when we talk about technology, we have to look into the device and usage of the device. Spintronics memory, I don't know too much. I know it is magnetic as well as the other I don't know too much of this, so I don't want to comment too much here. Obviously, spintronics means magnetic is there. That spin of electrons is play a big role there, and storing those in different way, the density of the memory cell or memory capacity, and making in memory computation or near memory computations, which indirectly talking towards AI, is also needed. The device creation is one side and use of the device another side. So, unless use is available, things will not go in hand. Today, simple hard disks is almost no use. PCs are coming with CCD or the static memory, which NVMe or anyone can say. One is capability NVMe, another is USB, you can say, connections or SATA connections. So, you have hard disks also comes with NVMe, the SSD, solid state device. So, this is another technology which we have to look into it, future point of view. And as I mentioned, only device is not issue. We have to look into the device with today's requirement, that is how much we can do most of the activities are in near the memory or inside the memory. In memory is tough, I know, because we do work on in memory, but it's for the TTL type technology or CMOS type technology. We know how difficult it is there, but near memory is already possible. Another is the storage class, storage in storage computing or storage class, which is the NVMe or CCD or SSD or whatever you can say. They have already near the store computations. Why I am putting computation in place? Because device future needs the computation also part of the auxiliary part or ancillary part of the memory. I am adding this because when you will discuss the program, I don't know, I have not seen the details, I don't know you are taking care of or not, but it is a necessity for survival of any technology. So,
in-memory computing is a part of it.
Part of it. So, it is a necessity now. It's a necessity now, but it's not that easy. whatever I know, it's not that easy. Device making is much easier than the coming to the IIT Guwahati. I think you know most of them. Now we are 30 years old, and we don't need any special things. But only things I wanted to say, whoever, wherever can join in IIT Guwahati, multiple activity, then online education and skilling. He will talk how online way you can participate. I am keeping that for him. But those who wanted to do offline program or our regular program, we have multiple options. Don't come and only spend here for the course. If possible, try to join some of the programs if you are ready to join, and programs are available in the web page. You can go and all, you can visit our labs and you can find it out. Those who are in online, please come and visit and look into our all possible programs, how you can be part of it. Those who are faculty, join. There are multiple options. You can collaborate with us. Options are plenty, including the joint research and projects, publications, irrespective of your organization have any agreement, that memorandum of understanding with IIT Guwahati, you can individually participate in any of the activity jointly with our faculty member or any research staffs. Those who just completed PhD, ready to come here and spend time, we have option for IPDF as well as several postdoctoral programs. Please join, enrich yourself, work with us, learn with us. We will also learn from you, and as a whole we can contribute to the nation building. Our nation is first. Everything is, we are part of the nation. Whatever we do, an end product is very, very important if possible, because we need in our indigenous effort for any activity. Maybe this Spintronics, this course of 10 days will be helpful for you to do a new directions in your career. With this, I conclude my talk. Thank you for listening.
Thank you so much, sir, for your insightful and encouraging words. Next, I would like to invite Professor Hemant B. Kaushik, sir, Dean of Online Education and Skilling, to kindly address the gathering.
Thank you. Professor Nandi, Director in Charge IIT Guwahati and Dean Administration IIT Guwahati. Professor Nemade, Head of the Department Electronics and Electrical Engineering. Our foreign expert, Professor Piramanayagam, who we can fondly call Professor Prem. Just now he informed us. And our own Dr. Tanmay Dutta, and my dear participants, along with my CET staff members. A very good morning to you all. I welcome you all to this beautiful campus of IIT Guwahati in a beautiful weather. This weather now is such that the temperature is about 20 degrees less than some of the other parts of the country. So you can enjoy this weather here. This is one of the most beautiful campuses in the country. So in addition to the grinding of 10 days in this Spintronics, I can't even pronounce it properly. I'm a civil engineer, but nevertheless I use memory in different forms. So in addition to the 10 days of grinding, spend some time outside, see different departments, what we are doing. We have 11 departments, 5 schools and 9 centers, about 450 faculty members, 8,500 students, though it is a vacation time now, but still you can find some around 3,000 to 4,000 students here. So roam around, see different departments and look for some collaborations. This GIAN program is not only about classroom learning. You must develop collaborations with the foreign expert, with the Indian expert and with all other faculty members and students, develop friendships with the other PhD students, those are here on campus doing different kinds of research. We have some state-of-the-art facilities in the campus. Please visit them and see where you can be involved, where you can collaborate with IIT Guwahati. There can be collaborations between your institutions and IIT Guwahati. This is one program. I think this year we are conducting about 14 or 15 GIAN programs, which is a very good number. Across the country, I think there are about 120, 130 GIAN programs being conducted this year. So you can imagine hundreds and thousands of students, working professionals, researchers, they are getting advantage of these courses. So it's a very good idea that was floated some 8 to 10 years back to have such kind of programs. Now, in addition to delivering lectures, the foreign experts are also involved in research in these institutions. They are also involved in some training programs. I'm not sure if there is any training program in addition to this program that is planned under this, but then we also have some programs in which there are additional training programs. There are additional MOOC development that is also a part of this. So the opportunities are endless. So we have conducted more than I think 30, 40 such courses in last 5, 6 years, 10 years. And then there are thousands of students who are the beneficiaries and who have then come back to us, like Professor Nandi was saying, that you come back, do further research here. So that is all possible. In addition to GIAN, the Center for Educational Technology offer many more skilling programs, skill development programs, reskilling programs. One is NPTEL. So I hope you know NPTEL. They offer almost free MOOCs to anybody. So we have developed more than, if I'm not mistaken, more than 600-700 courses on NPTEL. And these are offered freely. Only if you want to get a certificate, you need to pay a very small amount, take an examination and get the certificate. Every year, I think from IIT Guwahati itself, there are more than 1 lakh students who take these examinations every year. So it's a really, really popular program. More than 100 crore enrollments have happened in this NPTEL alone. So very popular program. Then there are skilling activities in many areas. So sometimes there are in-demand programs from the industries. Sometimes we offer program and we invite industries and colleges, institutions to take part. So the opportunities are really widely open here. IIT Guwahati has also started offering now online degree programs. One very popular program is BSc Honours in Data Science and Artificial Intelligence that we are offering since 2023. It is a 100% online degree program. Currently we have about 1720 students in just one degree in 2 years. So now the enrollment is open for the 3rd year and we already have received interest from about 4,000 students. So there will be an entrance examination. Those who have JEE advanced qualification, for them the admission is direct, no entrance. But for others there will be an entrance exam based on maths. So the Mehta Family School of Data Science and Artificial Intelligence is offering this program. This school also offers a very similar program as a BTech. So where the admissions are done through JEE Advanced. So the same set of faculty members who are teaching in this BTech program are also teaching in this online degree program. It's not only about degree. If you are interested in just having some advanced level of understanding in data science and artificial intelligence, then you can just enroll for 1 year and get advanced certificate. If you are more interested, in 2 years you can get a diploma, 3 years you can get BSc degree, and 4th year you have some capstone projects, some research. If you complete that, you get the full-fledged BSc Honours degree, which is equivalent to BTech degree, 4 years. You will be eligible to take GATE, you will be eligible to take MTech admissions, PhD admissions, everything is possible there. Now this is just one degree. From August this year, we are also offering online MTech in civil engineering, particularly to take care of the floods in this region, floods and river erosion. So this is a specialized degree developed for the government of Assam engineers. They will be coming here only for examination. Otherwise, it is all fully online. Then there is a online MTech degree that will soon be offered in robotics and artificial intelligence. This is again 100% online. So we have started the recording. So the way we conduct these online degrees is there are some recorded lectures which will be available to you. As per your free time, you can view them. Then there will be some live sessions where you can interact with the faculty members, the teaching assistants, the PhD students, ask questions. Then there will be weekly assessments. There will be discussion forum. There will be weekly assessments, and then of course there will be some end examination. So this is the way we conduct these online degree program. So these are the 3 programs that of course one is already running, 2 more programs will be offering in from this year. So I welcome you all to visit our web pages and see what we are doing. And if you are interested, join. If you know somebody who is interested, please spread the word. With that, I again welcome you all and thank you all for coming here and showing interest in this very interesting GIAN program. I hope your stay here is smooth, it is comfortable, and you will enjoy the beauty of the campus. Thank you.
Thank you so much, sir, for your thoughtful remarks and guiding us for many other programs which are running within the campus. So I would like to request the participant also to take a note on this. Next, I would like to invite Professor Harshal B. Nemade, sir, Head of the Department of Electronics and Electrical Engineering, to kindly speak few words with our audience.
Distinguished guests, Professor Prem, my colleagues and participants, on behalf of the Department of Electronics and Electrical Engineering, I welcome you all to this GIAN course on Spintronics memory. We know it's an emerging field, and though spin-based devices have great potential, the future directions are still unclear. So in such situations, a little advice from an expert can be enlightening and can become the guiding source. So today we have the opportunity to learn from a highly experienced person in this field. So I urge you to make most of this opportunity. And my advice to you is you try to learn beyond the simple information and techniques in this field. Rather, you try to discuss new ideas and try to get new directions from the experts. Finally, I hope that you will have pleasant stay at IIT Guwahati campus and a great learning experience to all who are present offline as well as online. Thank you.
Thank you so much, sir, for your insightful words. So before we proceed further, I would like to take the opportunity to introduce briefly about our distinguished foreign expert, Professor S.N. Piramanayagam, sir. Professor S.N. Piramanayagam is an internationally renowned expert in the field of magnetism with more than 3 decades of distinguished research experience in the magnetic materials and thin film technologies. He earned his PhD and doctorate degree from the IIT Bombay and has conducted significant research at the Shinshu University, Japan. Currently, he continues his impactful scientific works at Nanyang Technological University, NTU, Singapore, where he leads pioneering research in the advanced magnetic technologies with approximately 200 peer-reviewed publications and several international patents to his credit. Professor Piramanayagam has made notable and lasting contributions to the field of spintronics, magnetic recordings, and the neuromorphic computing. We are honored to have him with us today, and I now warmly invite Professor S.N. Piramanayagam, sir, to kindly share a few words with our audience.
Thank you for the kind introduction.
Good morning, professors and students. In any case, I am going to talk for 10 days with you, so I don't want to talk too much. I just want to say two things. Firstly, Professor Nandi told you that the electronics industry has grown from LSI to VLSI, GLSI, and so on. So somewhere around 20 years ago, the electronics industry found out that we cannot grow following Moore's law. Okay, so they were looking for technologies that can take the semiconductor industry from beyond Moore technology. So they were looking for many supplementary candidate or alternative candidates. So one such candidate is Spintronics. Okay, then somewhere in 2008 or so, the semiconductor industry started taking the semiconductor memory seriously, and they have started making products now. So now we have replaced eFlash with the STT-MRAM that you are going to learn in the next few days. So it is already a commercial product, and it's believed that the SRAM will be replaced by some of the Spintronic candidates in the near future. So that's also in the pipeline. So that is the kind of developments that we have in Spintronics. You will learn this in the next 10 days. Secondly, these days you can learn many things just by watching YouTube videos. Suppose you want to learn quantum mechanics, go to YouTube. There are so many channels teaching you quantum mechanics. You want to learn solid state physics, there will be so many courses in YouTube on solid state physics. But you may not find any such courses on Spintronics. Okay, so this Spintronics course I am teaching is a condensation of so many years of my knowledge. Like bee goes to many flowers, get nectars, then condense into honey and give it to us. So this course is basically, I have read so many papers. I have asked students to do presentation. So this is a condensation of many years of learning. So I hope you will actively participate and benefit from this lecture. So with that, I'll end my brief talk here. Anyway, I'm going to talk for the next 10 days. Thank you very much.
Thank you so much, sir, for your invaluable presence and inspiring thoughts. To formally conclude this inaugural sessions, I would like to invite Dr. Tanmay Dutta, sir, again for closing remarks.
Thank you, everyone. Thank you to all the dignitaries on the dais and Professor Prem as well, who has been kind enough to come over here and help us and spread his knowledge, share with us. So we look forward to that in the next 10 days. And thank you to all of you for being here today. And I hope, as I mentioned earlier, I hope you learn a lot. Okay, I look forward to interact with you. As some of them already mentioned, please feel free to move around the campus, visit departments. We can always help you. Talk to the PhD students here, interact with them, and we would like to see all of you to continue, because some of you are already, I know some of your faces, so some of you are probably already working in IIT Guwahati in different ways, as student, as interns, and so on. The rest of you, I welcome again, all of you, not only for this course, but all future endeavors that you would like to carry out at IIT Guwahati, and we look forward to that. Thank you. So with this, we end this inaugural session, and we have some snacks and tea arranged. Please have that, and then shortly we'll begin the first lecture session today. Thank you.
Let me start. Can you sit on a few more? Yeah, very good. Yes, yes. Yeah, yeah. I mean, I'm showing this one.
Sir, I think your night mode is on.
What mode?
Night mode, that in the display
yeah,
is a little
yeah,
bit
yeah.
on that side.
Okay. Anyway, we'll go to this.
It's fine here, but on the main
dark mode you have to remove here.
yes, it's turned it on.
What mode?
So they want to remove the dark mode from the stuff.
Check on
आप यहाँ पे check करवा के जाओ. Display में जाके
This one? Turn on.
night lighting.
night light. Turn off now.
Oh, okay. Okay, no?
So this is like the screen is smaller. And
Smaller because I'm duplicating. Shall we start? Ready? The equipment recording? Okay, thank you. Okay, good morning everyone. So, it is my pleasure to be here giving this GIAN course on Spintronics, memory, physics and technology. Usually I found the students in India to be very cooperative with the professor. They ask questions, they interact. So, I want the same interaction from you. Okay. Usually the energy the teachers get is from you. Okay. The energy we get is coming from you. So, if you pay attention, ask a lot of questions, then we also get excited, then we teach more. Okay. So, I would like to ask you all to ask questions, listen attentively, and with that let me get into the discussion today. So, this module is roughly going to be this way. So, we will have so roughly around 10% of this course will be the introductory stuff. Then we will move on to learn the fundamentals of magnetism, because magnetism is the fundamental needed for spintronics. Then I will touch upon magnetic recording, because magnetic recording is the parent technology for spintronics. So, if you ask me where the spintronics field is coming from, it is all coming from magnetic recording. So, people do research on hard disk drive and they invent so many things. All these are the founding seeds of the spintronics research that we are doing these days. Okay. So, I will touch upon magnetic recording a bit, then we will move on to the magnetic memory. Then towards the end we will learn some of the emerging technologies, like today Professor Dutta was mentioning, like neuromorphic computing, all these kind of things we will learn towards the end. Okay, why this module? Actually this slide was prepared for Singapore audience, but it's actually for anyone. So, if you know that the electronics industry is also picking up in India. So, there are a few plants coming up in Gujarat, and I heard that there is also some plants, semiconductor plants coming up in Assam and so on. So, semiconductor technology is a vital technology for all of us. The mobiles we use, the laptops we use, the memory we use, all are coming from the semiconductor technology. So, without semiconductor technology you cannot imagine how our life will be. Okay. So, it is very important concept, and as I mentioned early today, the semiconductor technology is also facing some limits. So, we cannot keep on increasing the processor size forever. So, the semiconductor technology is looking at alternatives. So, in that sense the spintronics field is very important. Okay. So, spintronics technology is supposed to extend the life of semiconductor technology. Okay. So, because of that this course is important. So, if you are here to learn some pure physics, then this is not the course for you. We are not teaching any pure physics here. In this course you will learn a bit of material science, how materials play a role in advancing the semiconductor spintronics technology, and how we can apply the material science principles to design the memory aspects for spintronics, and you will learn some applied physics, and I will also touch upon some electrical engineering concepts. So, by training I am not an electrical engineer, so I am a physicist, but I have some exposure to material science, electrical engineering and so on. Okay, so, these are the stuff that you will learn in this module. Okay, so, as I mentioned, interaction is very important, and I always feel very happy to talk to the student from India, because you all ask a lot of questions. So, in this course I will also ask a lot of questions. Okay. So, I will use this app WooClap. So, I will flash some questions. So, some of the questions will be of multiple choice. So, you just have to choose A, B, C, D. So, some case you may have to choose only one answer. So, for example, A may be right, C may be wrong. So, you just choose A, then you gave the correct answer. Some questions A, B, C, D, maybe there may be one or more right answers. Okay. So, based on the question that I flash, you may have to answer, either choose one or choose many. So, it is up to the question and the answer you think. Then there are also some questions where you may have to type in your answer. Okay. So, always keep your mobile ready, and when question comes up, you just choose the answer or type in your answer. Okay. So, I can see like how many have joined as of now, like looks like 48 of you have joined. Okay, let us start with this question as a trial. Why did you choose this course, for example? So, when you see this red light coming up, it means the question session is going to end. Okay, after you answer, I can basically flash. So, probably some of you have written, I want to learn gain spintronics knowledge or something like that. So, word cloud is usually a bit messy, but other questions you can see, like I will show you later. Okay. So, from tomorrow onwards, there will be a coherent story every day, one topic, but today it will be like scattered. Okay. So, it is like when you start cooking, what you do, you first collect the vegetables, you wash, maybe you peel the skin, then you cut the vegetables and keep it ready for cooking, right. So, today's session is like washing the vegetables, cutting the vegetables and keep it ready for cooking. So, whatever you are going to learn today are some of the miscellaneous things that we do not I mean things that do not fit into the regular flow of things. Okay. So, today is some kind of preparatory lectures that we will have. So, the first question today is name the first information storage system that the human beings have ever used. I want more answers, so I increased the time. Okay, many of you, I mean the words that look big are the majority of the answers. Okay, so many of you have chosen diary, so some of you have chosen calculator, some of you have written brain. Okay, so this is the answer that I expect. Okay, brain is the first information storage that the humans used. Okay, so since time memorial, we use our brain to know where we can get food, where a lion or something is going to come, where a predator is coming, so where we can hide. So all this information, I mean which food we can eat, which food is poisonous, so all those information from our life in caves and so on. So we used to remember everything using our brain. So that is the first information system that we used. But brain is not enough, right? So if I teach you so many concepts, you cannot take all the concepts in your brain, so you need to take notes. So right now we are taking notes in iPad or paper, but in the past people have used various other kind of information storage systems. So for example, people used clay to imprint letters, used rocks. Paper was invented in China, then people used palm leaf. Then when the computers came in, people used punch cards. Then people started using magnetic tapes, then magnetic drum, then followed by hard disk drive, floppy drive, and so many things. Okay, CD, now you use USB drive and so on. Okay, so all those information storage systems evolved because we need to somehow store the information. We cannot remember all the information, we need to store the information, so we need some storage systems. So that is why we invented so many other storage systems. Okay, so that is one point. To emphasize the second point, let me play this video. Okay, you can laugh. Okay, no need to like keep controlled. So what does this video tell you? Yeah, so when information goes from one person to the other person, there is loss of information. So traditionally our Indian system is not good. So we, let's say for example, we had a sloka or whatsoever, right? We never had a system of recording things on paper or anything. So we passed information from one generation to another generation just by asking people to recite. Okay, sometimes the information will get twisted. On the other hand, if you have like a Chinese system, you have a paper where information is recorded, then the information doesn't get lost. Okay, that's another point. Thirdly, like suppose you want to describe something. Let's say you go as a tourist to say Italy, you see something, then you come and tell your friend that I saw this, I saw that. Okay, you will tell something, but your friend will picturize something else. Okay, the information passed will be different. On the other hand, these days, you know, we all have Instagram, so many things. You produce reel, then your friend sees what exactly you saw. Okay, so these are all the importance of information storage systems. Okay. So they help you to remember, store the information, they help you to pass the information correctly from one person to the other person, even if it is visual. Okay. So, because of all these reasons, we need to look at the storage and memory systems. So, we have moved away from paper tapes to floppy disk, CD, USB drive. Now, we store information in clouds also. Okay. For example, you shoot a video, store it in YouTube. So, where is your video stored? It is stored somewhere in cloud. Okay. So, cloud is basically 80% hard disk drive and 20% semiconductor storage devices. So, because of all these reasons, it is good to know some working principles of magnetic recording based on hard disk drive, because whatever we store information, 80% of it is stored in hard disk drives. So, when I started teaching this course like 20 years ago, I wanted to show the students that the data grows every year. Okay. So, what I did, I just count the space used by my emails and I showed them that information grows every year. Okay. But these days you are all very familiar with the Facebook, YouTube, Instagram and so on. So, every day you shoot photos, upload to Instagram, shoot reels or shoot videos, upload them to Instagram, YouTube and so on. So, every day so many people are doing this. So, the information keeps growing. So, we need to come up with systems that can store all this information. So, this is a old slide, but as of 2018 about 10 power 21 bytes of information, I mean hard disk drives were shipped with a capacity of 10 power 21 bytes, but we are worried that we might generate more information than the capacity that can be stored by the hard disk drives. Okay. So, because of this reason we always want to improve the hard disk drives, and increasing the capacity of hard disk drives comes from Spintronics principle. Okay. So, Spintronics plays a very important role in how do we enhance the capacity of the hard disk drives. So, when I was like you, the hard disk drive I buy used to have like 1 gigabyte capacity. Okay. So, now you can easily buy 10 terabytes. 10 terabytes is like a 10,000 times larger capacity than what I used to buy in your age. Okay. So, this kind of capacity increase of the hard disk drives has come mainly from Spintronics. And as I mentioned, we generate lots of information, and a few years ago most of the phones used to have like a DVD kind of video, but now most of the phones have 4K USD or some phones have 8K USD. So, when you have this kind of capacity, basically you are generating, suppose you want to store 1 hour of uncompressed video in 8K USD format, you are generating 86 terabyte. Okay. So, all these things that we generate need lot of storage. So, that is where the storage is important, and memory anyway we are going to learn. So, memory is also important. So, quite often people get confused between what is memory, what is storage. Okay. So, people all think the USB drive you use is memory or storage. What is it? Storage. Yeah, the pen drive you use is a storage device, it is not a memory device. So, you can understand the difference between memory and storage by looking at the next few slides. Suppose you have an exam tomorrow. Okay, you have an exam tomorrow, say quantum mechanics exam, then you are studying for the exam tonight as usual. We all study just day before the exam, right? Then, so your desk will be filled with probably the quantum mechanics notes. Okay, nothing else will be on your desk. Okay. So, memory is like your desk. So, you keep the data that you need for your immediate work. Okay. So, that is the memory. So, in computer we have CPU, then we have memory. Memory is where the data that you want for your immediate computation is stored. On the other hand, hard disk drive or your pen drive or whatever storage device that you use is like the bookshelf or cabinet. Okay. So, you need all these books or files for your future. but you don't need them today. Tomorrow your examination is on quantum mechanics, so you don't need all this stuff. So but you need them for some other time. Okay, so you store them somewhere else, right? So the hard disk or the pen drive, all these things are like the bookshelf or cabinets. So depending on which is immediately needed, which is not needed immediately, we have a hierarchy in the computing systems. So if you look at the computer, you know that there is a CPU that does the computing, and the CPU fetches the information from cache memory. So this is a kind of memory. So whatever is very quickly needed, the information will be in cache, and if something is not that urgently needed, that's stored in random access memory. Suppose you are doing some computation, but say you also want your computer to store some movies which you don't need to watch, because tomorrow you have quantum examination. Okay, so you don't want to watch the movie, so the movie is stored somewhere in hard disk drive. Okay, so this is how the computing hierarchy look like. Whatever is immediately needed by CPU is closer. So CPU is the one that does the processing, cache is closer to the CPU, RAM is a bit far, hard disk drive is far, and the time needed also is like it takes around 10 milliseconds to fetch the data from hard disk drive, and if you look at the cache, it needs only 10 nanoseconds. Okay, so you can see that if the computer wants some information quickly, the CPU wants some information quickly, it wants to fetch from cache rather than from hard disk drive. And this also affects the cost. Okay, for example, hard disk drive can store a lot of information and it's very inexpensive. On the other hand, the cache memory or random access memory, they are expensive. So this is how the data is stored in your computers or in your mobile phone. Okay, let's do some questions. Okay, you can see the question, right? Okay, so this is how the results look like. So usually if most answers are, I mean if there is a wide distribution, right, for example like 33% answer this one, 33% answer this one, say 20% answer this one, 10% answer this one, that means the concept is not clear. But if majority of you answer one, most likely you are right. It is very unlikely that all of you are wrong. Okay, but so usually when I see a histogram like this, I don't need to spend much time because most of you have answered correctly. So in this case, the correct answer is the best CPU. Okay, so you only need a lot of computing power. You don't need to spend too much money on memory. Okay, so this is the correct answer. Next question. I think you can see the question in your phone. Okay, so here your supervisor asks you to do a job that handles and generates a lot of data. So in that case, you need both good CPU and a good memory. Okay. Also, you need the best hard disk drive because you need to store lots of data. Okay. So there will be some questions like this where you need to choose 2 or 3 answers. Okay. So depending on the question, you choose as many as possible. I mean, based on what you think is the right answer, choose. Okay, let's skip some questions. Now let's move on to the hard disk drive. So as I mentioned before, hard disk drive is the one where 80% of the data is stored today. Okay, so you might tell me that your computer or laptop doesn't have a hard disk drive. Okay, my laptop doesn't have a hard disk drive, or this Apple computer doesn't have a hard disk drive, but still we use a lot of hard disk drives for storing our information, because as I mentioned before, if you upload some video to YouTube, so Google stores your videos in some data center. So in a data center, 80% of the data is stored in hard disk drive. Okay. So if the data is not urgently needed, the data will be stored in hard disk drives. But some, for example, you take banks. Banks also store information in clouds. So banks may need the data for, suppose you want to draw money or you want to use phone pay, pay someone money. So that information has to be like brought very fast. Okay, those kind of information will be stored in solid state drives. Okay, so hard disk drives, as I mentioned, they are very important because 80% of our data is stored in hard disk drives, and hard disk drives were invented in mid 1950s. IBM International Business Machines, they invented hard disk drives in 1956. Since then it has been used in computers, and somewhere in 2000s it was also used in consumer electronics. So many of you might have seen, might be using iPhone. So before iPhone there was a product called iPod. Okay, I don't know how many of you have seen this. Okay, this is a music player. So before this we used to have like a tape recorders and so on, but this iPod was a revolutionary product because it came with a hard disk drive. At that time the small hard disk drive inside this iPod was storing 30 gigabyte of information. So with 30 gigabyte of information you can store like thousands of songs, which was a revolutionary at that time. You know, this was like 2005. That kind of time. So consumer electronics, it was they were also using a lot of hard disk drives. So there were video recorders which were using hard disk drives to store information, and even now Xbox uses hard disk drives. So when you play games, the games are stored in the hard disk drives of the Xbox. And now you have home cloud, you also have other cloud like Amazon, YouTube, Facebook kind of cloud. You can also have a cloud at your home. Okay, you can store information and you can access from anywhere. So all these things store information in hard disk drives. So if you open a hard disk drive, it will look something like this. Okay, so you will have a disk. So this disk is the one that stores the information. Okay, tomorrow I will settle this one. Today I will sit down. Okay, yeah, this disk is the one that stores the information. So in the disk you will have many tracks. Okay, so you look at this one. This is a circular disk. So you can have many concentric circles. So you call each of them as a track, like in a sports ground. You see many tracks, right? So in a similar sense, there are many tracks if you go from outer diameter to the inner diameter of a hard disk drive. So let us say I ask you, like, you go from here to here, say 1 inch. 1 inch is like this distance, right? The one segment of your finger. So you travel 1 inch. How many tracks you think you can find in a current hard disk drive? Roughly this is the size of a hard disk drive. I have hard disk drive, but today I forgot to bring. Tomorrow I will bring a hard disk. So let us say I go from this distance to this distance. How many tracks you think you can find? Give me some number. Millions. Okay, that's very close. We have around 500,000. Okay, so within 1 inch we can find 500,000 tracks. Okay, that. So when you say million tracks in 1 inch, what is the width of the track you expect? Huh? Micrometer? No. Huh? Tens of micrometer. Hundreds of nanometer. Micrometer and hundreds of nanometer. Okay. Yeah, typically right now the tracks are 50 nanometer small. Okay. So this width, the width of one track is only 50 nanometer. So that's the kind of density in which we store information. So remember, the first concept is that in hard disk drive we have many tracks. So in each track we can store many bits. For example, let us say from this line, this white line to this yellow line, let us say this is 1 bit, okay, then another bit and so on. So if you travel along the track, you will find many bits, and we have some number to describe all of them. Okay. So when you talk about some technology, right, you always associate some number with it. So for example, if you go to buy random access memory, you will go to the shop and order, say 8 GB RAM or 16 GB RAM, right. So RAM capacity is expressed in gigabyte. So similarly, when we talk about the tracks or the number of bits that we store in a given distance are expressed using some numbers. So here I show three such numbers. One is the track density. Track density means when you go from one end to the other end, how many tracks you have. So he answered 500,000, right. So if you have 500,000 tracks in 1 inch, so that's like 500,000 tracks per inch or 5 lakh tracks per inch. Okay. So this is one number that we use to define the technology. Okay. So if I ask you 8 GB RAM or 16 GB RAM, which one is better? You know the answer, right? 16 GB RAM is better than 8 GB RAM. So similarly, so we use this number, track density. So whether track density 100,000 tracks per inch or 200,000 tracks per inch, which is better? 200. We want more tracks in a given distance, right. So that we can pack more information. So track density is one number that we use to measure the technology, the growth of technology. The second number we use is the linear density. Linear density means, linear means what? Linear means a straight line. So I go from one end to the other end. So I count the number of bits in a given inch. Okay. So the number of bits in a given inch is called linear density, which means I go from here to here 1 inch, count the number of bits. So that's my linear density. So this is some number we use to define the status of a particular technology. Then the third number we use to define the growth of a hard disk drive is the areal density. So as the name implies, it has something to do with area, the density of bits in a given area. Okay. So you take a square inch. So in 1 square inch, how many bits you have? So that's called the areal density. So why I keep using the word inch is because the hard disk drive technology comes from America. America, they don't use kilometer, they use miles. They don't use centimeter or meter, they use inch, these kind of things. Okay. So since they invented hard disk drive, we have to deal with the inch. Okay. So we express the number of tracks, track density in number of tracks per inch, linear density in number of bits per inch, and areal density. So is a multiplication of linear density and track density. So is again the number of bits in a square inch. So these three numbers are usually in the research area. Common people don't talk about areal density or linear density or the track density. Common people talk in terms of capacity. Okay. So if you go and buy hard disk drive, or you order a hard disk drive from Amazon, for example, then you may order like 1 terabyte, 2 terabyte. Okay. So those numbers 1 terabyte, 2 terabyte, they all represent the capacity of the hard disk drive. Okay. So how much will be the capacity of the hard disk drive? That depends on, so that's a function of, so here what I want to say is capacity is a function of areal density. That means how many bits you can pack in a given area, then the size of the disk. Okay. So this disk can be big or small, so depending on the area of the disk you can store more information. And the third aspect is the number of platters. Okay. So in one hard disk drive you may have 1 disk or 2 disk or 4 disk. So depending on how many disks you have within a hard disk drive, you can increase the capacity. Okay. So people can play with all these things to increase the capacity of the hard disk drive. So I told you that when I was your age, we used to have 1 gigabyte hard disk drive, but now you can buy 10 terabyte hard disk drive. That's mainly coming from this aspect, by increasing the areal density. So previously we used to store, let's say 1 square inch, we used to store maybe like a few thousands of bits. Now we can store like a few terabits per square inch. Okay. So as of now, let me write it here. Okay, again let me settle this tomorrow. So currently the areal density is 1.5 terabit per square inch. So tera is like 10 power 12. So 1.5 times 10 power 12. So, that is like 1500 billion bits per square inch. So, that is the kind of areal density we have, and that is what we use for storing information in hard disk drives as of now. Yes. Yeah, please. Here?
You have mentioned the number of platters there.
Hmm.
So it means that number of disks.
Yeah, number of disks.
So these are arranged in the arrays manner, like one above the other.
Yeah.
So how this reading and writing will be done for the below one?
Okay. Yeah, this is why I suggested ask question. So when a teacher teaches you, right, the teacher will come up with 100 things to teach, but during the flow we might leave like 20% or 30% out. So unless you ask questions like this, we cannot bring everything. Okay, so thank you. So ask more questions like this. So first question was, what do I mean platter? Platter basically means I mean the disk. Okay, so the number of disk determine the capacity stored by a hard disk drive. The second question is, how do we write or read information from every disk? Okay, so here you see, okay, firstly before I answer that question, I also must say that the disk has two sides, right? So we use both sides to store information. Okay, so there is some set of information stored on the upper surface, and there is also some set of, almost equal number of information stored on the bottom side of the disk. So we use both sides to store information. So like writing on both sides of the paper. So sometimes you write on one side, sometimes you write on both sides, right? So when you write on both sides, you store more information. So similarly, we use both sides of the disk to store information. And in this visual, you can see only one arm. So this arm is the one that, okay, this arm moves like this. Okay, this spindle rotates the actuator like this. So this one goes from outer to inner side or inner to outside. So it can rotate like this. At the same time, the disk also will be rotating. So when you have a rotational motion and you have this arc motion of this, you can access the whole area. So that's how you read or write data onto the whole area of the disk. So there is another arm like this at the bottom also. So the bottom side also we have this arm, then there is a head that moves and moves over the bottom surface. Okay. So similarly, if you have like 3 or 4 disks, then you will have like 6 or 8 of them. So each disk has 2 of these actuators. Any other question? Pardon? Whether there is lithography involved in hard disk drive, the disk itself we don't use lithography. I'll give you some idea of how the disk is made during the next few days, but we don't use lithography for the disk, but for the head that reads or writes information, this small thing, there is some lithography involved. Any other question?
One question from the online participant.
Okay.
From the case one, the linear density is same for inner and outer track, as their circumferences are not same, I am asking.
The number of bits will be different, but the linear density will be more or less same.
Okay, one question from the Solanki, that can we say this is like a spin orbit coupling as analogy?
No. Why spin orbit coupling? No. Okay, I think time being I will say I think no, but I don't know if there is any deeper meaning. Let me come back to this later. But as of now, there is no. The answer is no. Okay, let's do some questions. So I taught you the linear density, track density, these kind of things. Let's do some questions. How do I get rid of the pen? I want to get rid of this.
This pointer.
No, I need to. Okay, I think this, now it's okay. Yeah. Okay, most of you are right. So when we measure the track density, we go from, say, the outer diameter to the inner diameter, count how many tracks we can see in a given inch. That's how we calculate. So 2 is correct answer. Okay, the answer is leaked. Okay, here the answer is leaked. So, but still you can try to calculate. Okay, I would have preferred a board, but we don't have a whiteboard, so I will read. Okay, so 1 meter, in 1 meter length, we are seeing 66 megabits, so which means 66 times 10 power 6 bits. Okay, but 1 meter is like 10 power 9 nanometer, right? So 1 billion nanometer is 1 meter. So in 1 billion nanometer, we have 66 megabits. Okay, which means 1 bit will be 1 billion divided by 66 million, so that will be like 15 nanometer. Okay, so the correct answer will be 15, not 50 or 20, 15 is the correct answer. Okay, let's do this one. Okay, I want more answers, so I extended the time. Okay, 2 million is the answer given by many of you. Okay, we can also say 2 megabits per inch. This is also correct. Okay, so since most of you have answered correctly, this is also correct. So I don't need to go through. Next question. Okay, majority of you are right. So 500,000 tracks per inch is the correct answer. For those of you who answered wrongly, so if you want to calculate the answer for this question, so 1 inch is 25.4 millimeter, right? So 25.4 millimeter is 2,540,000 nanometer. So you divide 200,540,000 nanometer by 50.8, you will get 500,000. Okay, so that's how we can calculate the track density. Okay, so for this particular course, I may not cover too much about magnetic recording, but I will give you a flavor of how the magnetic recording works. So, for example, whether we use lithography or we don't use lithography, what do we use, those kind of material science aspect I will touch up on in magnetic recording. Okay. So, it has been more than 1 hour. You want to take a break, maybe 5 minutes, short break. Okay. So please come back by 12:05. Now it's 12. Then maybe not charged.
Okay, so
Yeah, it's a USB,
this using battery or some
USB-C.
So I'll charge.
Yeah, you can charge it. Okay, let's continue. So far is the speed okay? Speed okay?
Yes.
Okay. The volume, can you hear back? Okay. And the comprehensibility, is it easy to follow? So far I think it's not tough, right? So you will learn some aspect of magnetic recording. Now let's move on to the next topic. So again today I am like giving you bits and pieces like cutting vegetable kind of thing today. So when I was your age again, I used to carry a Walkman to play music. So if I want to play games, then I should have a gaming device. Then if I want to watch movie, then there is a video.
Hello.
Yes?
No audio at all.
No audio. Okay, yeah. So if I have to shoot, take a photo, then I need to carry a camera, all those things, right? But now you can do all those things, all the things that we used to do with many different gadgets, with one gadget, which is your smartphone. Okay. So a smartphone can play music, it can shoot video, it can shoot photos, and you can play games, you can call people. All these were possible because of the concept that we learned this morning. So we were talking about Moore's law, right? So Moore is the co-founder of Intel. Intel is the one that makes the processors for your computers. So in 1965, Moore predicted, I mean he observed the trend that the transistors, number of transistors in a given chip was increasing twice every year. Okay. Then he predicted that this is how we should grow the semiconductor industry. That means we should try to pack double the transistors every year. Okay. So if you have like 1 million transistors today, next year we should have like 2 million transistors and so on. Okay. So this is something that he predicted, and this has been going on for many years. Okay. So until you can see until 2005 people are just following this Moore's law. Okay. The number of transistors that we have in a chip are doubling every year. So this has been possible due to the improvements in the lithography technique and also the semiconductor technologies, materials, physics, all those things led to this kind of progress. Okay. So because this progress, we have so many benefits. Okay. So in the past, like your computer has to be like very big, but now your computer is small, because you can make small processors that can do almost similar job or better job than the previous processor. Okay. So miniaturization was possible, and performance improves because you have more transistors in a given chip. So your chip is fast, it can do many more operations and so on. Then it can save power, and since you are packing more transistors in a given chip, the processing cost is the same. Okay. The lithography is the same, though the chemicals that you use for making transistor, the price is the same. Okay. But you pack more transistor in a given area, that means the cost you pay for every transistor is going to be reduced. And the new functions. So new function means previously your computer cannot play music, okay, long ago. So in 1980s the computer cannot play music, it can only do computation, but now your mobile phone can do so many things, right? So all those new functions were possible because of the following of Moore's law. Okay. So if you look at the number of bits in a micro SD card, for example, in 2005 you could store only like 128 megabyte, and 10 years later you could store 128 gigabyte. Okay. So 1000 times increase has happened. So this is like the 10-year challenge that you guys have in social media, right? So this is a 10-year challenge for the memory. Okay, so it has grown like 1000 times in 10 years. Okay. So all this is possible because of this Moore's law based growth. But as I mentioned during my introduction today, this cannot go on forever. So Moore's law also will face limitation. So there are many bottlenecks, and because of this reason the semiconductor industry started looking for alternative technologies. So we cannot rely on just silicon based semiconductor technology. We need to look for many other candidates. So one such candidate is a spin based system. Okay. So this is a very blue sky proposal. So people who are working on magnetism, they propose that you can make random access memory based on magnetic material, you can make logic based on spintronics material. That means you can replace the semiconductor technology completely with magnetic materials. This is a dream, but I don't think this will happen in the near future. But if you go towards some other area where it's possible that you can replace some memory with spin concept. Okay. So instead of SRAM, for example, SRAM is the static RAM, right? Static random access memory. So people are thinking of replacing static random access memory with something called SOT random access memory, spin orbit torque random access memory, which you will learn later. So people are looking at some alternatives like that, and this morning I told you that MRAM has already replaced eFlash. eFlash is also one kind of memory that you can find in your watches, phones and things like that. So MRAM has already replaced eFlash, but we are looking at using spin based concepts to replace or make it better, make the semiconductor technology better. So that's where the Spintronics is coming in. So what is Spintronics? You will learn more and more in detail, but as a beginning I can give you this cartoon kind of expression. For example, you take your phone, current phone, your mobile phone is only silicon based electronics, almost no Spintronics design here. So in this case you send electrons, it goes through the transistors, capacitors, resistor, whatsoever, and it comes out as the electrons, and you don't distinguish the electrons. Okay, so there is like some electrons flow in, they come out as electrons. So you don't distinguish between the electrons. Okay. On the other hand, this cartoon, I have two colors for electrons. Okay, I have a red color, I have a blue color for electrons. So now this is a Spintronics element. Okay, so you can notice that one type of electron, the blue type of electron, comes out more compared to red type. Okay, so now you can see that in this concept there are two types of electrons, and you have selectivity. So you can send one type of electron more preferably through your Spintronics elements. Okay, this is a very key cartoon level explanation of Spintronics, and later as we go more and more deep, you will learn what this blue and red color means. Okay. So I mean, to give you some analogy, for example, if you want to count the population of a country, we can say India has 1.4 billion. Okay, so you just count the number of heads, so you don't distinguish between how many males and females. So that's like the conventional electronics. So electrons, in the conventional electronics, we only consider the charge of the electron. So the electrons always have negative charge. So we only consider the charge of the electron in electronics. We don't count the other aspect, which is what we call spin. Okay, so we have studied in quantum mechanics that electrons have spin. So electrons can have up spin or electrons have down spin. and we do not consider that in the electronics, but we consider the spin property in spintronics. So, we will learn more of what is spin up, spin down, all these things, but you might have studied this already in your quantum mechanics, that electrons have a property called spin, and we consider this aspect also in spintronics. So, when I show the blue color, red color in my previous cartoon, basically I mean one type of spin, for example spin up, spin down, okay, that is what I mean. So, we consider the spin up, spin down property of electrons in the spintronics. So, this has its own benefit. For example, let us say you sell cosmetics, okay. So, which company will you choose? So, in one company there are like 100 males, 10 females. In this company there are like say 50 males, 50 females. Which company will you choose? Suppose you are selling cosmetic, which company will you go to, left or right? This one, right? Okay. So, knowing I mean cosmetic is usually targeted at female. So, you want to go to a company where there are more females. So, in this case this demography helps, right. So, this company has 110 people, this company also has 110 people. So, knowing that does not help you when you are selling cosmetic, but knowing which company has more females help you to sell more, right. So, in a similar sense, so when you also use the spin property, so you have some additional benefit, okay. So, that is what spintronics exploits. So, when you just consider electrons have only charge, then you are losing some of the benefits that you can have by considering the charge property, okay. So, spintronics considers the spin property also, okay. We can have this history another time. Let me go directly to so I will tell you all the story of spin another day. Today we will not go into that detail. So, there are many ways to explain what is spin. So, one, I mean the story which I am going to tell again another time. The spin property basically comes from quantum mechanical origin. So, people wanted to explain the spectroscopy, why there are two lines instead of one line, the spectrum, all those things. So, when people try to understand what is happening there, they brought this property, okay. So, they realized that electrons have this property called spin, okay. So, this is one definition of what is spin, okay. The second definition, which is wrong, but which is useful, is to imagine that the electrons spin around a certain axis, okay. So, if electrons are rotating counterclockwise, you can call one type of spin. If the electrons rotate in clockwise, you can consider as another type of spin. This is an inaccurate picture. So, let me repeat, this is a wrong picture, but this helps to imagine, okay. So, you can imagine that one kind of rotation is called spin up, another kind of rotation is called spin down. This is another way to understand spin. The third way to understand spin is like, so when you talk about electrical conductivity, right. So, when people studied electricity in 1700s, 1800s, they assumed that certain charges flow and the flow of charges are responsible for conductivity, okay. They did not know what is charge, okay. They just brought a term that charges flow and the flow of charges is the reason for electrical conductivity, okay. So, in a similar sense, you can consider spin, okay. Spin is responsible for magnetism. So, when you say magnetism, then there is spin. So, spin is responsible for magnetism. This is another way to understand what is spin. Then if all these arguments fail, all these explanations fail to make you understand, then accept spin as spin, okay. So, for example, when you studied electricity, your teacher taught you that electrons have charge, you did not ask what is charge, right. You accepted charge as charge, So, similarly accept spin as spin. Okay. So, this is how I can explain spin, and this is the meme that I use to explain what is spin. Okay, imagine a ball that is rotating, except spin is not a ball and it is not rotating. Okay. So, this is a meme way of explaining what is spin. So, we cannot explain what is spin using our known ideas. Okay. So, spin is a quantum mechanical property. So, just accept spin as spin. Okay. Okay, now earlier I draw a cartoon picture. Now, I come to a bit more detail. So, in the conventional electronics, we have circuits made of silicon, copper, all these are non-magnetic materials. Okay. So, when you send electrons through most of the non-magnetic materials, the spin property does not come into picture. So, the flow of electrons is spin independent. Okay. So, it does not matter whether it is up spin or down spin, it does not matter. Okay. So, that is why in the conventional electronics only charge plays a role, whereas if you take spintronics elements we will be using some kind of magnetic material. So, magnetic materials have magnetization, and there will be interaction between the spin and the magnetization of the material. As a result, the flow of electrons through magnetic materials will be spin dependent. Okay. So, we are using this spin dependent flow of electrons through magnetic materials for spintronics. Okay. This is a slight deviation. Very recently we also deal with spintronics. I mean, we observe spin dependent property in non-magnetic materials also. Okay. So, this is a very recent story, but for a basic understanding you can just consider these two pictures. Okay. In non-magnetic materials usually the electron flow is spin independent, and in magnetic materials the flow of electrons will be spin dependent. So, almost all the spintronic devices will have some kind of magnetic material. So, today your dean told you this, right. So, almost all spintronic devices will have some form of magnetic material, because in magnetic material the flow of electrons depend on the spin of the electron. Okay. So, in this course you will be studying about magnetic random access memory. So, in short MRAM. So, quite often I will use the word MRAM to represent magnetic random access memory. So, this is how the MRAM will be in a circuit, for example. Okay. So, we have some transistor and we have a device called MTJ, magnetic tunnel junction. So, this magnetic tunnel junction is the one that stores your bit 1 and 0. Okay. How it stores 1 and 0 you will learn later, but time being you just imagine that this particular device called magnetic tunnel junction stores bit 1 and 0. So, this is very similar to a DRAM. For example, in DRAM you have transistor and you have a capacitor, and this capacitor may be charged or discharged representing 1 or 0. So, we store information using this capacitor in DRAM, whereas in the case of MRAM we replace this capacitor with a device called MTJ. So, this MTJ can have high resistance or low resistance. So, you can call one of the state as 1, another state as 0. So, that is how we store information in MRAM. So, MRAM basically stands for magnetic random access memory. You can also call it magnetoresistive random access memory. So, in this course you will be learning more about spin transfer torque MRAM. This is the current spintronic memory. So, I told you that MRAM has replaced E-flash. So, basically the memory that replaced E-flash is a spin transfer torque MRAM. And as I showed you in the previous picture, this memory part contains a magnetoresistive element So, this MTJ or magnetic tunnel junction is the magnetoresistive element, and its resistance state can be made to be high or low, representing 1 or 0. Okay. And I mean, if you summarize the benefits and problems of various memories, yeah, every memory will have its own problem and advantages. So, in some areas MRAM can be useful, that is why the industry is working on this topic. Okay. So, in this course, you, as I mentioned, you will be learning about basic magnetism, magnetic materials, because these are the foundation for understanding magnetic recording or magnetic memory. And hopefully with the knowledge that you can have from this course, you can do your research better, or probably you can find a job in the electronics industry. So, that is the main objective of this course. Any questions so far? So, feel free to ask question anytime. So, sometimes okay. Flowing of spin is related to magnon. Okay, magnon is so in the case of magnon, you are talking about spin wave. Spin itself does not flow, but spin wave propagates. Flowing of spin need not be related to magnon. Okay. So, later you will learn more about this, how the spins flow, all these things you will learn later. Any other question from the audience here? How long you want to go today? I have material for another 2 hours, but maybe we can spend another 1 hour or 45 minutes. Okay. So, yeah. Yeah, I mean spin wave. Okay, for example, when we problem is we don't have a board. Okay, let me try to use action. For example, let us say we have a spin. This spin is precessing in certain angle. Then we have neighboring spin that has certain angle. So, if you trace the path of the spin wave propagation, you will find a wave like pattern. Okay. So, that is spin wave, and the magnon is the quantized quantum of spin wave. Okay. So, magnon is a concept. So, it is like phonon, photon. So, magnon is a quantum of spin wave, but spin is real, right. So, it is a concept, yes, yeah. Yeah. That's okay. Yeah, now it's working. Yes. Yes.
When you store information on the spin of the electrons, then if you make any memory device or a storage device based on it, then it would be very prone to environmental magnetic influences. Like when you bring any magnetic substance close to it, the information may be lost or changed.
Yeah, yeah. So, all this you will learn later. So, firstly, I mean when you talk about environment, there are 2 things. One is the temperature. So, at room temperature there is thermal energy, right. So, Boltzmann constant multiplied by temperature, there is some thermal energy. So, this thermal energy may disturb your spin, okay, whatsoever. So that's one thing. Secondly, like you said, magnet. Let's say I put my memory inside my pocket, also put a magnet, so that magnet may erase the information. So all these things you will learn later. Yeah. Any other question? So how do we understand spin wave? Is it the spin on different atoms arranged at different angles to call it a wave? Yes. And how do we understand the propagation of this wave? Okay, Magnon is not the topic of this particular course, but if you want to address this one, I can address in another class. Okay. I mean, this course we are not touching magnons, we are talking about spin, flow of spin, not the spin wave, but we can address this another day.
Sir, it will be drawback na, if MRAM will be comes in the range of the magnet and that data will be get erased.
Yes, yeah, this is a problem people are investigating. So the technical term is magnetic immunity. How you can make the MRAM immune to the external magnetic field. So this is a problem people are addressing. So if you go to say Global Foundries or some company which makes MRAM, so they develop studies to overcome this problem. Yes. But if you take hard disk drives, for example, hard disk drives you don't have this problem. Again I will explain why hard disk drive don't have this problem in another lecture when we go sequentially. Okay, so when you go gradually you will learn that. Okay. Any other question? Mm-hmm. I mean today I am just giving you a flavor. Okay, so you will learn all this in detail later, because now I haven't even taught you the magnetism. So if I teach you how the MTJ works, it will be difficult. I mean for some of you who have not learned magnetism, it will be totally difficult. So we will go with the flow. It will come in the later learning. Okay, so we are going to learn let's say MRAM, a bit of hard disk drive, how do we make sensors for hard disk drive and so on. So all these things, I mean there is some growth technique involved, technology involved. So this particular part we will be learning some of those bits and pieces of information. We can skip this. This one also I can see. So I talked about hard disk drive. Hard disk, there are so many processes. I am not going through all these things, but I will just describe this technique called sputter deposition, because this sputter deposition is the technique that is useful in the MRAM also. Okay, so let us learn about sputtering. So whether you make thin films for MRAM application or hard disk drive application, you always need something called substrate, because you are growing films with a thickness of 10 nanometer, 15 nanometer, or maybe about 100 nanometer. So those films are too thin, they cannot stand alone themselves. So you need to deposit on something solid. So that solid thing is called a substrate. Okay. So in the case of hard disk drive, people use many different substrates like aluminum alloy or glass substrates to store information. In the case of MRAM, the substrates are usually silicon. Okay, so you take a substrate, then on top of the substrate you deposit films. Okay, so how do we deposit films? So, we use this process called sputtering. Okay. So, what is the definition of sputtering? Okay. A simple definition is like playing billiards with atoms. Okay. So, we are basically playing billiards with atoms. So, in sputtering what happens, we have a material, for example, let us assume that this is a piece of cobalt and I want to deposit a cobalt film. Cobalt is a magnetic film, right. So, I want to deposit this cobalt onto the substrate. Okay. This is the, I mean, let us assume that this is the substrate on which I want to deposit cobalt, and so to achieve that I take a target which is also cobalt. So, this target I will collide with argon atoms. Okay. So, like in billiards what happens, you have balls hit the balls, then balls there is a transfer of kinetic energy, right. So, in a similar sense you use the kinetic energy of the argon atoms to knock certain other atoms. So, in this case cobalt atoms. So, the cobalt atoms will be ejected from the cobalt target and they will get deposited onto the substrate. Okay. So, that is words, right, that is lot of words, usually you do not understand if I keep on saying many words. So, let us use this video. So, in this case you can see the word target here. Okay. So, this target is the material from where we are getting the source. Okay. Suppose we want to deposit cobalt film, then all these atoms actually represent cobalt atoms. Okay. So, you have a cobalt target with a lot of cobalt atoms. So, this is the target and this is the substrate on which you want to grow the film. Okay. Initially to start with, this is just silicon oxide, nothing on top, but you want to grow the cobalt film on top of this substrate. Okay. So, what you do, you place the cobalt target in a vacuum system and apply certain potential. So, the potential is negative potential. So, this target is the cathode. So, it has a negative potential. Okay. So, when you have applied a negative potential, let us say you have argon gas in the chamber. So, let us say argon, due to cosmic radiation or something like that, argon is ionized, for example, let us say a few argon atoms are ionized. So, ionized argon atom is positive, right, positive argon ions, they will come towards this negative target. So, they will collide with this target, then knock off these atoms. So, these atoms will go everywhere. So, they will go here, 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 everywhere. Okay. And some of them will arrive at the substrate and get deposited. Okay. So, watch the video again. So, initially, oops, sorry. Okay, due to say some cosmic radiation or something, the argon has released one electron and it has become argon ion. Okay. Now, you have argon ion and your target is negative potential, it is a cathode. So, negative potential, so this positive argon ion will be attracted. Okay. So, this positive argon ion is attracted towards the target. Okay. And this argon ion has a kinetic energy, right, it has certain kinetic energy. Because of that, momentum transfer happens, the cobalt atoms from the target gets knocked off. Okay. So, this I mean you cannot control the angle of this argon collision, it will happen randomly. As a result, all these cobalt atoms will go in different direction. So, they will go in different direction. So, the substrate is on the path of this scattering of cobalt atoms. So, some of these cobalt will arrive at the substrate. Okay. So, when lots of cobalt atoms arrive at the substrate, you can say you have grown a film. Okay. So, this is called DC sputtering. So, DC stands for direct current. Okay. So, you apply negative voltage to the target. substrate is grounded. Substrate, chamber, all are typically grounded. Okay, so this is DC sputtering. So this is a pictorial description of what we learned before. So you have a target, you have a substrate. These two are inside a chamber. So it's inside a, you can say, a stainless steel chamber. So this chamber has to be at a certain vacuum. So to produce the vacuum, you have some vacuum pumps. So the vacuum pumps keep sucking the molecules, gas molecules inside this chamber. So you obtain vacuum, then do the sputtering. Okay. So we use argon as the gas for sputtering because suppose you want to deposit cobalt onto your substrate, there should be no chemical reaction. So you are starting with a cobalt target and you want to get cobalt film. So you do not want any chemical reaction. For example, you use oxygen, then you try to sputter cobalt, you will get cobalt oxide. Okay. Or you use nitrogen, you will get cobalt nitride. Okay. So you do not want reactive gases. So if you want to deposit cobalt as cobalt, you want some inert gas. Okay. That is why we use argon. People can use krypton, xenon also, but they are expensive. Okay. So normally people use argon for sputtering, and this power supply supplies the negative voltage to the target. Okay. Target is called a cathode. Okay. It is at a negative potential, that is why it can attract the argon ions. So argon is neutral, but once you remove one electron, it becomes a positive argon ion. So the positive argon ions will go towards the target and they will knock off the atoms from the target. Okay. So this is a sputtering process. This is another video animation again. Now it tells you the whole thing. So we have a chamber. So inside this chamber we are going to do sputtering. So inside the chamber there are a lot of gas, say let us say atmospheric nitrogen, whatsoever gas is here. So at first what you do, you pump all these gases out. So you apply, use some pump and pump all these gases out. Okay. So typically we evacuate the chamber to pressures of 10 power minus 8 torr or 10 power minus 9 torr, something like that. So after we reach very low base pressure, we can send in argon. So now argon is flowing in. So this blue color gas is argon. Okay. So we send in argon gas. Pump is also on. Okay. Then we apply, power is on, then the plasma forms. Okay. You can see a plasma, which means the sputtering is happening. Okay. So during the plasma formation, what happens is that the argon atoms knock the target, and the target atoms shown by the red color, they go everywhere, and they get deposited on the walls also. So they will get deposited on the walls of the chamber, they go everywhere, and they will get deposited on the substrate also. Okay. So this is called DC sputtering. Any questions so far about sputtering?
There are two more questions.
Yeah.
So, if the sputtering is same like the PLD, if yes, then which one is preferred?
Okay. Sputtering is different from PLD. Which one is preferred? Okay, this is a very interesting question. I always criticize PLD. Okay, no industry uses PLD. All the labs in India probably use PLD because it is cheaper to buy, and for research it is okay to use PLD. But if you want to make reliable devices, for example, if you take hard disk industry, they make hundreds of million disks every year, say billion disk every year. All disks have to perform similarly. Okay. So if you want to achieve this kind of performance consistency, then sputtering is the best technique. Okay, so in sputtering you can control the thickness, uniformity, composition, uniformity, all this uniformity you can maintain very well. So sputtering is the industry friendly technique, not PLD. But PLD is good for university because it's easy to build.
Second question is the cobalt in the sputtering reaching and making the film like the nucleation on the substrate? Will the mean free path will play a role in this?
Yeah, I mean it will nucleate, yes, the grain growth of the cobalt films depend on the nucleation and so on. Mean free path also will play a role. For example, if you, I mean we deposit films under certain argon gas pressure, right. So let us say you have 3 millitor argon or 30 millitor argon. So in one case you have fewer argon gas molecules inside the chamber. So when you have 30 milliliter argon, you have more argon molecules in the chamber. So the mean free path will be different depending on the pressure of argon gas inside the cylinder, and that will affect the film quality. Film will be different, film property will be different. So if you deposit at low pressure, the film will be more uniform because the mean free path is less. The arriving atoms have more energy. So when they arrive at the film surface with more energy, they tend to form more uniform film. On the other hand, if the mean free path is low, when the atoms arrive at the substrate, they come with very low kinetic energy. So they do not travel around much. So you will have like more rougher films. Okay.
Does the substrate type will play any role in the use of why they are using it?
Okay. So if you are talking about Spintronics, Spintronics is an extension of silicon electronics, right. So we are using silicon substrate. So that is why we are using silicon substrate. So Spintronics is an extension of electronics, conventional electronics, everything is based on silicon. So we use silicon substrate. In the lab we use silicon oxide. I mean we have silicon coated with silicon oxide, we use silicon oxide in the labs, yes. But in the hard disk industry we do not use silicon oxide or silicon. In the hard disk industry, as I show, I mean I skipped some slide because we are not focusing on hard disk. So in hard disk industry we use many different substrates like aluminum alloy, glass substrates, all these things. Depends on the application. Which substrate you use depends on the application. Yes. Yeah.
Any minimum pressure required to form the plasma inside?
Yes. Yeah. So if you are okay, so the process, as you understand, initially we pump out all the gas. Okay, so we reach a very low base pressure, say 10 power minus 8 torr or 10 power minus 9 torr, something like that. Then we let argon gas in. So if argon gas pressure is too low, then you cannot form plasma. So the formation of plasma, like you see in this video, is when you form plasma, basically the sputtering happens. Okay, so the plasma cannot be formed if the argon gas pressure is too low. So typically depends on your design of a sputtering machine. Some machine you can sputter at 1 millitorr or something like that. Below 1 millitorr it will be tough. Okay, so we can say minimum is like 1 millitorr or 3 millitorr depending on how the sputtering machine is designed.
It will be difficult to sustain the plasma.
Yeah. If you go too low argon pressure, it will be difficult to sustain the plasma. Yes.
What happens to the argon ions after it knocks off the target?
It will go somewhere. It will be in the chamber, and it will be, I mean, it's a dynamic process. So you let argon gas into the chamber, and you are also pumping at the same time. So some argon will be going around inside the chamber, some will be pumped out. So there is a continuous flow. Yes.
In the sputtering process,
Mm.
what happens if I reverse the direction? My cathode is, my target is at the top and my substrate is at the bottom.
Mm.
So now the same process, I am keeping the same potentials at the negative point. So will the gravity will play any role for deposition?
Gravity may not play much role because you are talking about atoms, they are like very very light, right? Gravity doesn't play much role.
Information in the top and the bottom, let's say replacing the thing, that will be same.
Because of certain other advantages, people choose one way or the other. For example, in my lab all the guns are facing up, and one advantage of the gun facing up is, for example, let's say you have certain, let's say you have cobalt target, then you want to study the doping of cobalt with something. Let's say you want to dope gadolinium into your cobalt and study how the property of cobalt gadolinium will perform. Okay. So one simple way to do this is like place a chip of gadolinium on cobalt. Okay. So you have a cobalt target, place a gadolinium chip, then now you deposit cobalt gadolinium film, right. So this is easy to achieve if your target is facing up. Okay. So there is some advantage if target is facing up. There is also disadvantage if target is facing up. For example, let's say your target is facing up, you grow a lot of film, you have a shutter accumulates a lot of film. At some point of time this will fall onto your target. So over a period of time your target also gets contaminated from the peel that comes out of your shutter. So this problem can be avoided if your target is facing down. Okay. So there are advantages and disadvantages of target facing up or down. So in some industry they have targets facing this vertically like this, then substrate goes in between. So hard disk industry is like you have targets at the side, then your substrate goes in vertically. So depends. So which one is better or not depends on the case. Any other questions? Yes.
Can laser be used for this sputtering process instead of current?
Yeah, that is this process, PLD, pulse laser deposition. So people shine laser onto a target. So the laser generates a plasma. So that's a totally different technique. Yeah.
For magnetism related studies, other than silicon substrate, what substrate can be used?
For which one?
Magnetism related studies,
Mm,
characterization. Other than silicon substrate, what we can use?
Yeah, you can use anything.
Only silicon?
No, you can use
quartz?
anything. You can use anything. Depends on your application. For example, you can use a glass slide.
Okay,
You don't. I mean, you don't need to use silicon. You can use the slide glass, right? The one used in the microscopy. Microscopy glass. You can use that. So I have used that. So silicon we can use.
Quartz?
So
Quartz?
quartz also you can use. So for some studies we use sapphire. Some studies we use magnesium oxide. So depending on your application, what do you want to do, you have to choose the proper substrate. Yeah. Any other question? Okay, so far what I described was a DC sputtering. Now I move on to a slightly advanced type. It's called DC magnetron sputtering. Okay. So in the DC sputtering we apply direct current to the target and we generate plasma, but there is a problem. In that DC sputtering without magnetron, usually you need very high voltage, around 1000 volt is needed to strike plasma. Also the deposition rate of DC sputtering is low. Okay. So to improve the deposition rate and to achieve sputtering at lower voltage, like for example 400 volt or something like that, people use this concept called DC magnetron sputtering. Okay, so in this case we have a target, below the target we have certain arrangement of magnets. So these magnets generate a magnetic flux, or you can say magnetic field, and you know that that Lorentz force. So when electrons have certain velocity, so charged particle moving with certain velocity, and when they are in a magnetic field, they have this V cross B force. Okay. So I can show you this video to make it interesting.
So this is an evacuated tube, and it puts a big negative potential on this electrode. So high that it actually boils the electrons come off the electrode. It makes just a beam of electrons. It also has some a little bit of background gas that ionizes to keep everything stable and doesn't charge up too much. But mostly you have electrons flying off this electrode, and most of them go straight to this metal plate, and that's the end of the story. But there's a little slit in the plate, so some of them get through and make a beam that keeps going. So you've got a beam of electrons, and this little plate is tilted a little bit, so they slowly, along this direction, they crash into the plate. The plate has a phosphor on it, so it lights up when they crash into the plate. So when I turn it on, there you can see the beam. That's a beam of electrons flying through the tube. So what we're going to do is bring a magnet and see what it does to the beam of electrons. Because remember, this bar magnet, the field lines go from the north pole, the red is the north pole, to the south pole. So if we just think about the poles or the field right at the ends, because we're going to use the ends, it'll be this way near the north, it'll be pointing in the south. So I will bring the north pole pointing at me at the beam, and let's see what that'll be. We have the beam going this way, and I'm going to bring this pointing in, so we're going to have a B field like this. So V cross B also the same as this. It should be up. So let's see what happens. There's our beam, and I bring in this magnet. Oh, there's the deflection we hoped for, but it's dead.
Okay, he said the beam should go up, right? But the beam came down. Why?
Charges of electron.
Yeah, because he didn't consider the charge of the electron, negative charge, right? So because of that, there is a deflection in the down direction. So we use this. So we use this V cross B force. So what happens? Let's say now this is the target. So this is a piece of cobalt that we want to deposit. In the previous case, we didn't have the magnets below the target. Now we have magnets below. So there is a magnetic field. So when there is a magnetic field, and when now we have electrons, so these electrons will spiral around. Okay, because of the V cross B force, electrons will be spiraling around these flux lines. So when electrons spiral around here, means they spend more time. Okay, they spend more time near the target. So when they spend more time near the target, they have more probability of colliding with argon atoms. Okay, then they can produce more ions. Okay, so the spiraling of electrons lead to more ionization. Okay, so when you have more ionization, basically we are applying voltage, right? The current will be large. Okay, so this is what I am talking about. So more ionization means we can sputter at lower voltages. So compared to DC sputtering, which happens at around 1000 volt, with magnets below the target, we can reduce the sputtering voltage to 400 voltage. And because of this V cross B force, we learned that there will be more ionization, which means the deposition rate can be increased. So we can form thicker films in shorter time using this DC magnetron sputtering.
I can actually.
Okay. So that is the concept of DC magnetron sputtering. Let us do some question before we move to the next topic. Okay, most of you are right. So, as I mentioned, substrate is a material platform to hold layers of thin film, and it can be a piece of silicon wafer, or it can be a piece of glass slide, or it can be a single crystal of magnesium oxide, aluminum oxide, anything. So, all of the above is the correct answer. Good. Okay, we skip this one. Okay. Most of you are right. So, in DC magnetron sputtering, we keep an array of magnets below the target. Okay. So it will be something like this. Okay. For example, in the earlier picture I showed you, like we have one set of magnet here, another set of magnet here. So, let us say this is north pole, this is south pole, there will be magnetic flux going from this to the other side, which can generate the magnetic field needed for the magnetron sputtering. But for industry application, people do not prefer this. Okay. I mean, if you go to your lab and look at the magnetron in your lab, probably it will be like this. Okay. There is a problem with the magnet configuration like this. Can anyone say what is the problem? Let us say you have a magnet like this below your target, what will be the problem? I mean, if the magnets are strong, you can still sputter, or if your magnetic target is thin, you can still sputter. But there is another problem with this design. What happened? Yeah. So what happens in this configuration, the more erosion happens in this region. Okay. So, I mean, the magnetic field goes this way, there is more probability for electron to stay here. So, more ionization in this region, more sputtering happens here. So, after some time what happens is your target will be it will be like this. Okay, let us say you look at one side. So, because of more ionization here, the target will be eroded here, the rest of the target is not used much. Okay. So, after some time what happens, you will burn a hole, then you have to throw the target. Okay. So, basically you will be using maybe 20% of the target, the remaining target is spoiled. Okay. This may be okay for the labs, but if you are looking at the industry where they make many pieces of say memory or disk, it is not acceptable. So, they want to use the target as much as possible. So, to do that they have this kind of asymmetric array. Okay. So, here is symmetric, right, the magnets is symmetric with respect to any line you draw from one edge to the other edge, but here it may be symmetric with respect to this line, but it is not symmetric with respect to this line. Okay. So, they use this kind of asymmetry configuration. So, if this is not rotating, then more etching happens here, right. So, you can see this is where the magnetic field will be strongest, and you see the etching will be mostly here, but they will use this asymmetric magnet array and rotate below the target. Okay. So, when they rotate below the target, for example, it can be like this. So, asymmetric array, but they will rotate behind the target. So, in that case they can erode the target more uniformly, and this can help to use the target significantly, and it also helps in achieving the uniformity in thickness. Okay. So, these are some techniques people use for depositing thin films for hard disk or MRAM. I think I can skip this part. Okay, I also want to teach you some aspect of material science, because later when I talk about MRAM, MTJ, I will be talking about some crystallographic fundamentals. So, I need to introduce this one, but because it is very late now, I will stop here. Maybe we will continue from here tomorrow. Okay.
So we talked about this GDCO, this is a ferromagnetic material.
Gadolinium cobalt is a ferrimagnetic material. Yeah, this ferrimagnetic material generates strong orbital torques. Now we want to tune the sign and the magnitude. Can we do that by changing gadolinium content only or cobalt? Temperature of what? Temperature of deposition or temperature of operation?
So he is asking that if I want to increase the magnitude of the ferromagnetic that particular material, so like the temperature also plays important role in that or not. And the second thing is asking is that
temperature of deposition.
And the content of the GD and cobalt if I am varying, the magnitude will be increased or not.
Okay, maybe you can ask this question. This is about orbital torque, right? We will be discussing spin orbit torque, orbital torque, etc. maybe on day 7. So, at that time he can ask this one. Maybe I answer this question: why is sputtering of soft magnetic materials difficult as suggested? Maybe I can draw a picture. Can they see? Okay. So, let us say this is the audience in Teams. Can you see the PowerPoint? Please type yes or no. Now they can see. Okay. Let us say this is a target, normal target. Normal means non-ferromagnetic. So, if you have magnets below, then these are, I mean these targets have not much permeability. So, magnetic field will go above the target. So, we will see lots of flux lines. So, with non-magnetic or of materials with a low permeability, you will see lot of flux lines above target. So, you can achieve lot of V cross B force. So, sputtering is not a problem. On the other hand, if you have a ferromagnetic material like a soft magnetic material and you have magnet below, so because of the permeability of the ferromagnetic material, most of the magnetic field from the magnet will go through the magnet, the target itself, and only few flux lines will come out. Okay. So, for example, if you measure the magnetic field here, it could be like say 300 to 500 oersted, something like that. On the other hand, if you use the same magnet and soft magnetic target, here if you measure the field on top of the target, you will see that it is like 50 oersted or something like that. Okay. Very low field above the target because of the permeability of the soft magnetic target. Okay. Soft magnetic target conducts all the flux through the target itself. So, nothing comes out. So, the field is very low. So, because this field is very low, you cannot sputter. So, typically we need around 300 oersted or more to achieve good DC magnetron sputtering. Okay, any other questions? Yeah, I mean this question is related to the same thing, the gadolinium cobalt. Any other question? Okay, if not, we stop here and we will continue from here tomorrow. So, tomorrow we will learn a bit of material science, then start learning the fundamentals of magnetism. Yeah, thank you. Bye bye.